Hi, welcome back. Let us now discuss our Module 2 about the fundamentals of symmetrical components. A symmetrical components is a modeling technique that permits systematic analysis and design of three-phase systems. Decoupling a detailed three-phase network into three simpler sequence networks reveals complicated phenomena in more simplistic terms. Sequence networks results that can be superposed to obtain the three-phase network results. Assume now that we have three voltages designated as BA, BB, and BC. They are given. And these three sequence networks are classified as the positive sequence network, the negative sequence network, and the zero sequence network. Now, what is a positive sequence network? Positive sequence networks are phasors, three-phase balance, and have the same phase sequence as the original set of unbalanced phasors. For the negative sequence phasors, these are three-phase balance but having a phase sequence opposite to that of the original set of unbalanced phasors. The zero sequence, on the other hand, are single phase equal in magnitude and in the same direction. The key idea of symmetrical component analysis is to decompose the system into three sequence networks. The networks are then coupled only at the point of defaulted unbalanced point, that is at default. The positive sequence sets have three phase currents or voltages with equal magnitude, with phase B, as shown in the figure, lagging phase A by 120 degrees and phase C lagging phase B by 120 degrees. And for the negative sequence as shown in the diagram, the sequence networks have three phase currents or voltages with equal magnitude, with phase B leading phase A by 120 degrees and phase C leading phase B by 120 degrees. So you have the vector diagrams as shown. And lastly, for the zero sequence network, so these are sequence sets having three values with equal magnitude and angle. So you have the BA0, BB0, and BC0. As an illustration, we have here three unbalanced voltages, BA, BB, and BC. They are phase voltages that are unbalanced, unequal in magnitude, and they are not 120 degrees apart. And decomposing this into three sequence networks, for the positive sequence networks, we have BA1 leading BB1 and BB1 leading BC1, and all these are equal in magnitude and 120 degrees apart. Whereas for the negative sequence network of this phase voltages, they are equal in magnitude, of course 120 degrees apart. BB2 is leading BA2 and BA2 is leading BC2. So these are the negative sequence of voltage BA. And for the zero sequence voltages, all the sequence of voltages BA0, BB0, and BC0 are equal in magnitude and directed in the same direction. Now, combining all these sequence voltages, the positive, negative, and zero sequence voltages, this figure shows the vector sum of the sequence components of the decoupled unbalanced phasors of voltages. Now, as an illustration, so this is for the sequence set representation, any arbitrary set of three phasors, say IA, IB, IC, can be represented as the sum of the three sequence sets. IA is equal to IA0 plus IA plus IA minus. IB is equal to IB0 plus IB plus IB minus. IC is equal to IC0 plus IC plus IC minus. These parameters, these are the zero sequence network, IA0 plus IB0 plus IC0. For the positive sequence set, these are the IA plus IB plus IC plus. For the zero sequence set, these are the IA minus plus, or the IB minus, IC minus. Then, conversion from sequence to phase source. Only 3 of the sequence values are unique: IA0, IA plus, IA minus. The others are determined as follows, using the operator A, wherein A is equal to 1 angle 120 degrees. A plus A square plus A cube is equal to 0. A cube is equal to 1. So thus, IA0 equal to IB0 equal to IC0, since by definition they are all equal. Now, how do we convert from sequence to phase source using the A operator? The AB plus can be written in terms of IA. So using the operator A, AB plus is equal to A squared IA plus. IC plus is equal to A IA plus. IB minus is equal to A IA minus. And IC minus is equal to A squared IA minus. So all these representations of the parameters can be written in matrix form. You have the IA, IB, IC in that left side of the matrix is equal to a 3 by 3 matrix multiplied by the 3 by 1 matrix. Now, the 3 by 3 matrix is composed of the elements 1, 1, 1, 1, A squared, A, 1, A squared. Thus, the phasor matrix IA, IB, IC is equal to the product of the A matrix and the sequence phasors, IA0, IA plus, and IA minus. So, defining the symmetrical components transformation matrix, so as defined in the previous slide, A is equal to, A matrix is equal to the a 3 by 3 matrix composed of the following elements: 1, 1, 1, 1, A squared, A, 1, A squared. So, then, IA, IB, IC, these are the phasor currents, equal to the A matrix multiplied by the sequence currents matrix, IA0, IB, or IA0, IA plus, IC minus. So, by taking the inverse, we can also convert from the phase values to the sequence values. The sequence currents now will be equal to the inverse of the A matrix multiplied by the phase currents, or the phase values of the currents. Now, the A inverse is now equal to 1/3 of that 3 by 3 matrix. This time, the elements will be composed of 1, 1, 1, 1, A squared, 1, A squared, A. So, sequence sets can also be used with voltages as well as currents. So, now, we have here an example wherein the current phasor IA, IB, IC is equal to these magnitudes. IA, 10 angle 0 degree. IB, 10 angle negative 120 degrees. IC, 10 angle 120 degrees. So, these are unbalanced phasors. So, we convert this into sequence currents. So, based on our previous discussion, the sequence currents is equal to the inverse of the matrix A multiplied by the phasor current matrix. So, thus, the sequence currents will be equal to 1/3 multiplied by the inverse of matrix A multiplied by the phasor current IA, IB, IC. So, solving for this, multiplying these two matrices, we now have the sequence currents to be equal to 0, 10, angle 0 degree, and 0. So, if we now interchange the magnitude of IB and IC we can now have the sequence currents to be equal to 0, 0, and 10 angle 0 degree. So it means that IA 0 is equal to 0, IA positive is equal to 0, IA negative is equal to 10 angle 0 degree. And similarly, for voltages, we have here BA, BB, and BC to be given as 5 angle 90 degrees for BA, BB is 8 angle 150 degrees, and BC 8 angle negative 30 degrees. So these phase voltages are unbalanced phasors, unbalanced voltages in a given system. So we want this to be converted into sequence voltages using our previous discussion of the A matrix and the phase voltages. So the sequence voltages will be equal to the product of the inverse of the matrix A and the phase voltages. So multiplying this, so we now have the sequence voltages to be equal to BA0 to be equal to 1.67 angle 90 degrees, and BA positive is equal to 3.29 angle negative 135 degrees, and BA negative is 6.12 angle 68 degrees. Now, let us consider a Y-connected load. So, as shown in the diagram, the Y-connected load have impedances, phase impedances of equal magnitude, say Y. And at the neutral point, we have a neutral impedance, say N. And the load is connected to a source, a balanced three-phase source, wherein line currents will be flowing for each line, IA, IB, and IC. And this line currents will be flowing to the neutral point of the Y-connected load, going to the neutral impedance, and this current will be equal to IN. IN is now equal to the sum, the vector sum of IA, IB, and IC. Now, if we want to get the voltage between phase A to the ground, denoted as BAG, that is equal to the drop across the phase A, that is IA multiplied by ZA, plus the drop due to the neutral impedance, IN, ZN. Now, simplifying this, we know that IN is equal to IA plus IB plus IC. So, if we substitute IN to this equation of BAB, we can simplify the equation of BAB. BAB now is equal to the quantity ZY plus ZN multiplied by IA plus ZN plus or multiplied by IB plus ZN IC. Then similarly for BBG, that is equal to the product of the drop due to the phase B and the neutral impedance. And substituting IN to that equation of BBG, we can arrive at an equation for BBG to be equal to ZN IA plus the quantity ZY plus ZN multiplied by IB plus ZN IC. And for BCG, that is now equal to ZN IA plus ZN IB plus the quantity ZY plus ZN multiplied by IC. Now, these three equations, BAG, BBG, and BCG, can be written in matrix form. On the left hand of our equation in matrix form, we have the BAG, BBG, and BCG matrix. Equal to, we can have the same matrix to be composed of ZY plus ZN, 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 ZY plus ZN, 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 and ZY plus ZN, multiplied by the current matrix IA, IB, and IC. Now, having our knowledge on about matrices, the voltage equal to current matrix multiplied by the same matrix, and likewise by Ohm's law, voltage equal to the current multiplied by the impedance. Likewise, the sequence voltage equal to the matrix A multiplied by the phase voltage, and similarly for the current, the sequence current equal to the A matrix multiplied by the phase current. Now, this given matrix BAG, BBG, BCG is equal to the same matrix multiplied by IA, IB, IC. If I get now or multiply an A matrix to this equation, to this matrix, I can have now BS on the left side of our equation to be a sequence voltages to be equal to, on the right side, a sequence current. If I'm going to consider now the impedance matrix to be multiplied by A matrix and the inverse of the A matrix. So A inverse and the product of A and the impedance is now equal to this 3 by 3 elements composed of the elements say Y plus 3 say N, 0, 0, 0, say Y, 0, 0, 0, and say Y. So these are the elements of the inverse of A matrix, the Z matrix, and the A matrix. Now, as shown in the previous slide, so we now have our sequence voltage matrix to be equal to the Z matrix, which is equal to the product of the A inverse, the Z matrix before, and the A matrix multiplied by the sequence currents IA0, IA plus, IA minus. Now, if we're going to simplify this, we can solve that B0 is just equal to say Y plus 3 say N multiplied by I0. I plus and I minus is 0 for B for that voltage B0. And B plus is just equal to say Y multiplied by the positive sequence current. And B minus is just equal to say Y multiplied by the I minus or the I negative. Now, this B0, B plus, and B minus can be represented by a sequence network. For the B0, that will be equal to say Y in series with the neutral impedance 3 say N. And the current that will be flowing will be equal to I0 connected to a voltage B0. And for the positive sequence network, that will be equal to a simple network composed of say Y. The current flowing will be the positive sequence current, and the voltage there is equal to the positive sequence voltage. Then for the negative sequence network, so you have that the say Y in that network connected to a negative sequence voltage, and the current flowing will be the negative sequence current. That's all for our module 2, and see you in our next module.